In this lesson, you will be learning the concept of ensemble learning. By the end of this lesson, you will be able to explain ensemble learning, evaluate the performance of boosting models. Overview. Ensemble technique combines individual models together to improve the stability and predictive power of the model. This approach permits higher predictive performance compared to a single model. Ensemble finds ways to combine multiple machine learning models into one predictive model in order to decrease variance using bagging, decrease bias using boosting, or improve predictions using stacking. Let's understand the ideology behind ensemble learning. As you have seen before, certain models do well in modeling one aspect of the data, while others do well in modeling another. Instead of learning a single complex model, learn several simple models and combine their output to produce the final decision. In ensemble learning, the combined strength of the models offsets individual model variances and biases. Ensemble learning will provide a composite prediction where the final accuracy is better than the accuracy of individual models. Ensemble methods can be divided into two groups, sequential ensemble methods and parallel ensemble methods. In sequential ensemble methods, base learners are generated consecutively, that is, AdaBoost. The basic motivation of sequential methods is to use the dependence between the base learners. By weighing previously mislabeled examples with higher weight, the overall performance of a model can be boosted. Parallel ensemble methods are applied wherever the base learners are generated in parallel, for example, random forest. Since the errors are often reduced dramatically by averaging, the basic motivation of parallel methods is to use independence between the base learners. Here in the given diagram, we are using parallel ensemble method where the different models work best in one or other aspect of data. They are combined in the ensemble model where the best aspect of each of the models is considered upon the input data, and then ensemble learning model comes up with the predictions. Ensemble model is the application of multiple models in order to obtain better performances from a single model. Performance depends on two major factors, robustness and accuracy. Ensemble models incorporate the predictions from all the base learners. This provides robustness. Ensemble models deliver accurate predictions and have improved performances. Ensemble Learning Methods Part A. You can create an ensemble by combining all weak learners. Once weak models are properly combined, we can obtain more accurate and/or robust models. You can also create an ensemble of well-chosen, strong, and diverse models. By combining data from numerous modeling approaches, ensemble models gain more accuracy and robustness than a fine-tuned single model can gain. Model averaging is an approach to ensemble learning where each ensemble member contributes an equal amount to the final prediction. In the case of regression, the ensemble prediction is calculated as the average of the member predictions. In the case of predicting a class label, the prediction is calculated as the mode of the member predictions. In the case of predicting class probability, the prediction can be calculated as the argmax of the summed probabilities for each class label. A limitation of this approach is that each model has an equal contribution to the final prediction made by the ensemble. There is a requirement that all ensemble members have skills compared to random chance, although some models are known to perform much better or much worse than other models. A weighted average ensemble is an extension of a model averaging ensemble where the contribution of each member to the final prediction is weighted by the performance of the model. The model weights are small positive values, and the sum of all weights equals 1, allowing the weights to indicate the percentage of trust or expected performance from each model. Now let's take a look at what bagging is. The idea behind bagging is to combine the results of multiple models to get a generalized result from a single model. Bagging or bootstrap aggregation reduces variance of an estimate by taking the mean of multiple estimates. There are 3 steps to perform bagging. Step 1 is to create randomly sampled data sets of the original training data, bootstrapping. Step 2 is to build and fit several classifiers to each of these diverse copies. Step 3 is to take the average of the predictions to make a final overall prediction. Ensemble Learning Methods Part B. Let's understand how random forest is an ensemble learning model. Random forest is a good example of ensemble machine learning method. Random forests, as one can guess, combine various decision trees to produce a more generalized model by reducing the notorious overfitting tendency of decision trees. Random forests are utilized to produce decorrelated decision trees. It creates random subsets of the features. Smaller trees are built using these subsets, creating tree diversity. To overcome overfitting, diverse sets of decision trees are required. Boosting is a sequential process where the errors of the previous model is corrected by each subsequent model. Let's assume an example of different types of body pain and their diagnosis. Headache, stomach pain, and leg pain will have a different reason. Let's assume that X causes headache, then X will not cause leg pain because Y causes leg pain. These 2 variables are not the reason for stomach pain. Stomach pain will be caused by variable Z. Depending on the results of weighted opinions, the doctor will suggest the diagnosis sequentially. Let's understand the way boosting works in the steps flow. Step 1 is to train a classifier H1 that best classifies the data with respect to accuracy. Step 2 is to identify regions where H1 produces errors and weighs to them and produces a H2 classifier. Step 3 is to aggregate those samples for which H1 gives a different result from H2 and produces H3 classifier. Repeat Step 2 for a new classifier. Let's understand what AdaBoost is and how it works. Let's first understand boosting. Boosting is a technique of changing weak learners into strong learners. In boosting, each new tree is a fit on a modified version of the original dataset. AdaBoost is one of the first boosting algorithms to be adapted in solving practices. AdaBoost helps you mix multiple weak classifiers into one strong classifier. Let's understand this through a scenario. Consider a scenario where there are plus and minus symbols indicating the data points. We will try to understand AdaBoost workflow. Working of AdaBoost. So the first step is to assign equal weights to each data point and apply a decision stump to classify them as a plus or minus. The most suited and most common algorithm used with AdaBoost is a decision tree with one level. These trees are short and solely contain one decision for classification. They are often called decision stumps. As you can see in the given graph, decision stump D1 has generated a vertical plane at the left side to classify the plus. A decision stump is a decision tree. It uses only a single attribute for splitting. For distinct attributes, this typically means that the tree consists only of a single interior node. Now apply higher weights to the incorrectly predicted 3 plus as shown in the given graph and add another decision stump. You can see that the size of 3 incorrectly predicted plus is bigger than the rest of the data points. In the second step, the second decision stump, D2, will try to predict them correctly. So as you can see, D2 has classified 3 misclassified plus correctly. D2 has also caused misclassification error to 3 minus. In the next step, D3 adds higher weights to 3 minus. A horizontal line is generated to classify plus and minus based on higher weight of the misclassified observation. In the final step, D1, D2, and D3 are combined to form a strong prediction that has complex rules as compared to the individual weak learners. AdaBoost Algorithm and Flowchart. Now, since you know the workflow of AdaBoost classifier, let's understand the AdaBoost algorithm. A weak classifier is prepared on the training data using the weighted samples. Only binary classification problems are supported. So every decision stump makes one decision on one input variable and outputs a plus 1.0 or minus 1.0 value for the first or second class value. The misclassification rate is calculated as error equals correct minus n divided by n. In the given equation, error is the misclassification rate. Correct is the number of training instances predicted by the model, and n is the total number of training instances. So let's understand the steps involved in this algorithm. Step 1, initially data points is weighted equally with weight. Wi equals 1 over n, where n is the number of samples. Step 2, a classifier h1 picked up that classifies the data with minimal error rate. Step 3, the weighted factor alpha is dependent on errors et. Step 4, weight after time t is given as this formula, where z is the normalizing factor, h1x, yx is the sign of the current output. Let's understand the flow of AdaBoost algorithm. It follows the following steps. 1. Initially, AdaBoost selects a training subset randomly. 2. It iteratively trains the AdaBoost machine learning model by selecting the training set based on the accurate prediction of the last training. 3. It assigns the higher weight to wrongly classified observations so that in the next iteration, these observations will get a high probability for classification. 4. Also, it assigns weight to the trained classifier in each iteration according to the accuracy of the classifier. The more accurate classifier will get higher weight. 5. This process iterates until the complete training data fits without any error or until it reaches the specified maximum number of estimators. Gradient boosting. Now let's understand gradient boosting. Gradient boosting trains several models in a very gradual, additive, and sequential manner. The major difference between AdaBoost and a gradient boosting algorithm is how the two algorithms identify the shortcomings of weak learners, that is, decision trees. GBM minimizes the loss function MSE of a model by adding weak learners using a gradient descent procedure. Gradient boosting involves 3 elements. 1. A loss function to be optimized. 2. A weak learner to make predictions. 3. An additive model to add weak learners to minimize the loss function. Let's understand the GBM mechanism. Gradient boosting trains many models sequentially. Each new model gradually minimizes the loss function of the whole system using the gradient descent method. So in y equals ax plus b plus e, E needs special attention because it is an error term. The learning procedure consecutively fits new models to produce an additional accurate estimate of the response variable. The principal idea behind this algorithm is to construct new base learners that might be maximally correlated with negative gradient of the loss function associated with the whole ensemble. So let's understand the working gradient boosting. GBM predicts the residuals or errors of the prior models and then sums them to make the final prediction. Step 2, one weak learner is added at a time, and existing weak learners in the model are left unchanged. Step 3, GBM repetitively leverages the patterns in residuals and strengthens a model with weak predictions. Step 4, modeling is stopped when they do not have any pattern that can be modeled. Let's look at the steps involved in GBM algorithm. Step 1, fit a simple regression or classification model. Step 2, calculate error residuals, that is, actual value minus predicted value. Step 3, fit a new model on error residuals as target variable with the same input variables. Step 4, add the predicted residuals to the previous predictions. Step 5, fit another model on residuals and repeat steps 2 and 5 until the model is overfit or the sum of the residuals become constant. Xgboost. Let's understand extreme gradient boosting. It is a library for developing quick and superior gradient boosting tree models. Xgboost is one of the implementations of the gradient boosting concept. But what makes it unique is that it uses a more regularized model formulation to control overfitting, which gives it better performance. Thus, it helps to reduce overfitting. Extreme gradient boosting is a custom tree-based algorithm used for classification, regression, and ranking with custom loss function. It has interfaces for Python and R that can be executed on Yarn. Xgboost is extensively used in ML competitions as it is almost 10 times faster than other gradient boosting techniques. Let's understand the Xgboost library features. Xgboost library tools are built for the sole purpose of model performance and computational speed. Let's look at system features followed by algorithm features. We will finally take a look at the model features of Xgboost. System features are parallelization. Parallelization. It produces tree construction using all CPU cores while training. Distributed computing. It uses a cluster of machines in order to train very large models. Cache optimization. Data structure involved in Xgboost makes the best use of hardware. Algorithm features are sparse aware. Algorithm behind Xgboost provides automatic handling of missing data values. Block structure. It supports the parallelization of tree construction. Continued training. Its algorithm provides continued training in order to boost an already fitted model on new data. Model features are gradient boosting. It uses gradient boosting machine algorithm, including learning rate. Stochastic gradient boosting. It does subsampling at the row, column, and column per split levels. Regularized gradient boosting. It does regularization using both L1 and L2 regularization. Xgboost parameters. Part A. Let's understand the Xgboost parameters. General parameters consist of a number of threats that help to prepare data. Task parameters correspond to the objective that helps to build a model. Evaluation metrics help to predict and visualize the predicted values. Booster parameters consist of a step size that evaluates the prediction performance metrics and ROC curve and regularization that compares the prediction performance against the logistic regression model. Let's understand the general parameters of Xgboost. General parameters guide the overall functioning of Xgboost. So let's understand what these general parameters are. nThread is used to define the number of parallel threads we are going to use. If no value is entered, the algorithm automatically detects the number of cores and runs a thread on all the cores. Booster parameters guide the individual tree or regression at each step. There are two types of boosters. Which booster can you use? GBtree uses tree-based model. GPLinear uses linear function. Usually, a tree booster outperforms the linear booster. Silent default equals 0 is used to print the running messages. If the silent parameter is set to 1, no running messages will be printed. Hence, keep it 0 as the messages might help in understanding the model. Let's look at the booster parameters. Booster parameters give the individual booster tree regression at each step. Let's look at the parameters for tree booster first. ETA defines the step size shrinkage used in update to prevent overfitting. After each boosting step, you can directly get the weights of new features, and ETA shrinks the feature weights to make the boosting process more conservative. ETA range is between 0 and 1, and the default value is 0.3. Gamma defines the minimal loss reduction required to make a further partition on a leaf node of the tree. The algorithm will be more conservative when the gamma is larger. Its value ranges from 0 to infinity, and the default value is 0. Max depth is used to define the maximum depth of a tree. Its value ranges from 1 to infinity, and the default value is 6. Min child weight is used to define the minimum sum of instance weight needed in a child. If the tree partition step results in a leaf node, with the sum of instance weight less than min child weight, then the building process will give up further partitioning. In linear regression task, this simply corresponds to the minimum number of instances needed in each node. The algorithm will be more conservative if the min child weight is larger. It ranges from 0 to infinity and the default value is 1. Xgboost parameters. Part B. Max delta step is used to set the maximum delta step allowed in each tree's weight estimation. If the value is set to 0, it means there is no constraint. If it is set to a positive value, it can help make the update step more conservative. Usually, this parameter is not needed, but it might help in logistic regression when the class is extremely imbalanced. Its value ranges from 0 to infinity and the default value is 0. Subsample is used to calculate the subsample ratio of the training instance. Its value ranges between 0 and 1, and the default value is 1. Call sample by tree is the subsample of ratio of columns when constructing each tree. Subsampling occurs once for every tree constructed. Its value ranges between 0 and 1, and the default value is 1. Now let's understand the parameters for linear booster. Lambda defines the ridge regression regularization term on weights. Increasing this value will make the model more conservative. The default value is 0. Alpha defines the lasso regression regularization term on weights. Increasing this value will make the model more conservative. The default value is 0. Lambda bias defines the ridge regression regularization term on bias. Increasing this value will make the model more conservative. The default value is 0. Now let's look at the task parameters. Task parameters guide the optimization objective to be calculated at each step. The objective options are binary logistic, defines logistic regression for binary classification whose output is probability, not class. Multi-softmax defines the multi-class classification using softmax objective. Evaluation metrics for validation data. A default metric will be assigned according to the objective RMSE for regression, error for classification, and mean average precision for ranking. The evaluation metric options are RMSE, log loss, error, AUC, mirror, MLO gloss. Demo Pima Indians diabetes. Problem statement. The objective of the dataset is to diagnostically predict whether or not a patient has diabetes based on certain diagnostic measurements, including in the dataset. All patients are females of at least 21 years of age and of Pima Indian heritage. The dataset consists of several medical predictor variables and one target variable, outcome. Predictor variables include the number of pregnancies the patients have had, their BMI, insulin level, age, and so on. Let us import the required libraries, including pandas and model selection from sklearn. Also, we will import AdaBoost classifier from sklearn.ensemble to further optimize our model. Import pandas, import sklearn import model _ selection. From sklearn.ensemble, import AdaBoost classifier. Now load the dataset with a pandas data frame. Extract the values from the columns in the form of an array. Set the random seed value as 7 and number of trees as 30. We will build classifiers using AdaBoost and Xgboost. Let's create the AdaBoost model using scikit-learn. AdaBoost uses decision tree classifier as the default classifier. Pass the model within the cross-validation score function to evaluate the results using the cross-validation technique. Construct the model now by splitting the trained test indices into 10 consecutive folds. Again, evaluate the model such that each fold gets used once as a validation while the remaining 9 folds form the training set. Print the results. AdaBoost gives an accuracy of 76%. Similarly, we apply the Xgboost algorithm. Import the respective modules, namely SVM and XGB classifier. From sklearn, import SVM. From Xgboost, import XGB classifier. Initialize the XGB classifier under the name CLF. Set the seed value as 7 and number of trees as 30. Construct the XGB classifier using the k-folds technique such that number of folds equals 10. Evaluate the model using the cross-validation score, similar to the way we did for AdaBoost classifier. Again, the accuracy is around 77%. We have shown only 2 classifiers. You can use different classifiers and compare the results. Also, check results after applying 10-fold cross-validation. Great, we have seen how to apply boosting algorithms to classification. Let's quickly recap the steps we covered. 1. Build models using AdaBoost and Xgboost. 2. Compare the accuracy of classifiers. Model selection. When do you need to evaluate the model performance? Models can be evaluated based on measures of performance. Model evaluation aims to estimate the generalization accuracy of a model on future data, that is, unseen, out-of-sample data. So model evaluation techniques are used to evaluate the model's performance when there is a chance of evaluating new data that is unseen or out of sample. Let's now look at how to access model performance. Train, test, split, or cross-validation split are the techniques used to evaluate the model performance. Train, test, split divides the training data set into 2 sets and uses the first training set to train the model and tests the model using the second set. Cross-validation split splits the data set in 2 sets, namely train and test, and then calculates the accuracy of each set and finds the average of the results. Let's look at how train, test, split works. So we have a given data sets that we need to split into training data and testing data. Split the data randomly using negative and positive symbol. Now, when you have training data randomly selected from the given data set, the remaining data falls under the test data. Move this data into the hypothesis space. Make sure that your test set meets the 2 subsequent conditions given. The test set must be large enough to yield statistically meaningful results. The test set must have different characteristics than the training set. Now verify the result by matching the trained data with the test data. Now test the training data individually with respect to the test data present in the hypothesis space. Wherever the data that has the same symbol matches, it provides accurate result. Prediction given here is 9/13, which shows the matching prediction. Common splitting strategies. So let's understand what percentage of data should be used for training and for testing. So we can use either of the 2 common splitting strategies to split the data. K-fold cross-validation or leave one out. Let's first understand how k-fold cross-validation works. The procedure contains a single parameter referred to as k and points to the number of groups that a given data sample is to be split into. As such, the procedure is usually referred to as k-fold cross-validation. When a particular value for k is chosen, It's going to be employed in place of k within the relevancy of the model. So how does the leave one out technique work? This approach leaves one data point out of the training data. That is, if there are n data points in the original sample, then n1 samples are used to train the model, and 1 point is used as the validation set. All the combinations are created in this way. The original sample can be separated, and the error is averaged for all trials in order to provide overall effectiveness. Now let's understand the difference between train, test, split, and cross-validation. Advantages of cross-validation. 1. It is a better estimator of out-of-sample accuracy. 2. It provides a more efficient use of data since each data is used for training and testing. Advantages of test, train, split. 1. Runs k times faster than k-fold. 2. Simpler than k-fold, so it would be easier to analyze the testing errors. Demo cross-validation. Problem statement. A few learners have implemented random forest classifier on the iris data, but better accuracy can be achieved by using the cross-validation sampling technique. In this analysis, we will generate the random forest using the cross-validation splitting technique. Let us import the inbuilt iris dataset from the sklearn.datasets library. From sklearn.datasets, import load_iris. Load the dataset with a data frame. Extract the input data. Similarly, extract the target values. K-fold cross-validation. Use the K-fold cross-validation technique to split the dataset into k consecutive folds without shuffling by default. Here, we will split the dataset into 5 consecutive groups. From sklearn.model_selection, import K-fold. Using a for loop, we will now iterate the individual train test sets within the input data. Let's now split the data set into 10 consecutive folds. Using a for loop, we will now iterate the individual train test sets within the output data. Let's initialize the random forest classifier. From sklearn.ensemble, import random forest classifier. Import the cross-validation score library from sklearn and get the model evaluated for accuracy by using the cross-validation score parameter. From sklearn.model_selection, import cross_val_score. The accuracy of the classifier is 95. Great, we have seen how to apply cross-validation to split the dataset. Let's quickly recap the steps we covered. 1. Shuffle and split the dataset randomly into K groups. 2. Summarize the skill of the model using model evaluation scores. This brings us to the end of Ensemble Learning. You are now able to explain Ensemble Learning, evaluate the performance of boosting models.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.